So as you look through page 300, we are going to end up identifying properties of perpendicular bisectors and angle bisectors, and more specifically, that's going to be in a triangle. In a triangle. All right, so the first thing you did was fold up a whole bunch of stuff, triangles, and we noticed that the bisectors of the angles do something. And what did you notice? They all intersect. And that's probably the most basic thing you noticed. Well, it turns out that the perpendicular bisectors of a triangle, they also intersect. Now, there's going to be something more about it, too. Something more besides just intersecting. And then from that extra property we get, we can come up with a name for these points. What's special about these points? What's special about the places where they intersect? I want to define three things. Number one, what does the word concurrent mean? It's the point where the lines intersect. When we actually do the perpendicular, so this first one here is the perpendicular bisectors. Is that the right? Yeah. Perpendicular bisectors. So when you perpendicular bisect it, so notice what's true. AY is the same as YC. Next, this one right here, that means XB and AX are the same size. And same thing down here. So we have perpendicular and bisectors. They all meet at a very, very, very nice place, very clean. But there are two nice things that happen about a perpendicular bisector. So what's a circumcenter? The circumcenter is the point of concurrency. Spell right. Of the perpendicular bisectors, and it is equidistant from the vertices. Yes, from the vertices. So to say that again, the point of concurrency of the angle bisectors, so that's what the circumcenter is, and it is equidistant, it being the circumcenter, is equidistant from the vertices. So how do I mark that here? This point right here, point P, is equidistant from every single vertex there. So from P to B, from P to C, and from P to A. It's exactly in the center of the vertices. In the center of the vertices. Now notice what that actually also happens. Since PC is the same size as PA is the same size as PB, notice that if I were to use this as a radius, what would happen? I would get a perfect circle that touches each vertex. And this is why it's called the circum, because circum means to go around. Like if you're circumventing a situation, you're going around it. Circum means to go around. So it's the center that creates a circle that goes around the triangle. All right, so this next one here, what we want to do is also try using coordinates. We want to find the circumcenter of the triangle. So one thing we want to probably start with is take our points 2, 7 and 10, 7 and 10, 3 and plot them on the coordinate plane. I'll also form the triangle like so. Now I'm going to label the coordinates after I label the coordinates of the midpoint. So the midpoint we can calculate, but what's nice is that for some of these we can actually just count to find the midpoint. Clearly this one here is a midpoint because it's 2 above C and 2 below B. And this is my midpoint because it is 4 away from those two. And it looks as though that one's my midpoint right there. It does say to label these, so I'm going to choose some letters, M, N, and O, like so. Now the perpendicular bisector of AB goes through M. Turns out it also goes through O. Then the perpendicular bisector of BC goes through N. And lastly, so does this one, but notice that they all intersect right there at what we called O. So the point of intersection of the bisectors is going to be at 6, 5. 6, 5, right there. This problem here. A town planter wants a bench that's equidistant from 3 trees in a park, okay? So here are 3 trees, or it could be a bathroom that's going to be close to 3 different buildings, or whatever the case may be. So here's a tree, and here's a tree. They're going to put a bench somewhere. Where should I put that bench? I have an infinite number of opportunities to put it. However, but only one of them is going to be equidistant. Only one bench is going to be equidistant from every single tree. So how do we do that? Well, we form the triangle. And since this is my circumcenter, I'm going to do the perpendicular bisectors. Now, using tools of geometry, we can actually make those, but I'm just going to sketch those for this activity here. So this is about halfway through, and I'm going to go like this. So that's going to be true. Continue on, and if I attempt it on this one here, this is about the midpoint right there, and then perpendicular it, boom. Notice I don't have to do it for the third one. Why not? Because I already know that the third one, when I do that, it's going to cross right there. So once I have that point, I don't need to draw another one. So where should the bench be? The bench should be right here at the circumcenter. Where should the bench be? At the circumcenter. And how do we make that? We use the perpendicular bisectors. By the way, it might be helpful to try to remember, well, how do you make the circumcenter? So I was trying to figure out a way that could be helpful. So the circumcenter is almost as long as the word perpendicular. So maybe that's one way to help remember. It's like the same size, right? In terms of a word. So how do you make the circumcenter? You perpendicular bisect everything. So that could be helpful if you find you can't remember where that comes from. All right, so there is one application, is that we want to find an equidistant point from from 3 different locations. A, B, and C. We found that the park bench should be approximately there. This next pretty point of concurrency is derived from the angle bisector. So this bisector here cuts this big angle C in half right there. Same thing over there, and they all intersect at this point right here. They all intersect at that point right there. So there's part of it is what is the point of what is the incenter? The incenter is the point of concurrency of the angle bisectors of the sides. Of the angle bisectors of a triangle. And the incenter, is equidistant from the sides. So notice how this is not quite a converse, but it's kind of flipped around. The circumcenter, when you find it, that one's equidistant from the vertices because you cut the sides in half and you get equidistant from the vertices. This one, you cut the angles in half And now you're equidistant from the sides. So another cool thing, which means this, that this YP, XP, and ZP are all congruent. So this could be kind of like roads that are connecting to three places. So this is the road AC, this is a road BC, and this is a road. And you want to place something that's equidistant from the roads so that you don't have to travel far off your route. You don't have to travel far off your route. If I'm going, boom, now I can come back. Boom, something like that. So this would be a nice position to put something that's shared off the roads between connecting two towns or three towns. Something like that. So that is called my incenter. And if you have a hard time remembering that, like I do, how it's made, well, incenter, I just say something like angle bisector. Or angle is kind of a short word, and incenter is shorter than circumcenter. So that could be helpful. And if it doesn't, find something that does help. Okay, so over here at this diagram, let's analyze what's happening with this diagram. Notice here's KM, and it is the angle bisector of that angle. And then here is LQ, and it is the bisector of the big angle L. And it intersects at this point right here. So what can I now conclude? I know that this Q is the incenter. Yuck. And therefore I know this, that QO, QN, and QM are all the exact same size. So because of that, we're asked here to find out what the value of X is, or first we have to find out X is to find out what QO is. But I already know that because Q is the incenter, these two are going to be exact same size. So 5X plus 36, is equal to 2X plus 51. And then X is 5. Not done, because I have to put that back into, and it doesn't matter where I place it, because QN, QM, and QO are all the same size. So as long as I put 5 back into one of those, I get my result. So that means QO happens to be 61. And we don't know what the units are, if it's miles or inches or whatever. So Q is my incenter because I angle bisected there.